Hello everyone. Today we will discuss chapter 3 in THERMO II class, or chapter 8 in the textbook. The title is Gas Power Systems. This is the learning outcomes of this chapter. The first one is to conduct air standard analysis of internal combustion engines based on Otto and diesel. So we should be able to sketch PV and TS diagrams and evaluate property data at principal states. So pretty much similar to the one we did in chapter 2. And then apply energy, entropy, and exergy balance. I put different color for this exergy just to differentiate with the learning outcome we had in THERMO 1. And then to determine net power output, thermal efficiency, and mean effective pressure. And then to conduct air standard analysis of gas turbine power plants based on the Brayton cycles and its modification, including the ability to sketch TS diagram and evaluate property data at principal states. And then to apply mass, energy, entropy, and exergy balance. So here we have additional parameter mass, because in the second system it is a control volume. So there will be a mass flow in and out of each component in this gas turbine power plants. And then to determine net power output, thermal efficiency, back work ratio. So this parameter, we know this in the previous chapter, and the effects of compressor pressure ratio on performance. This is the content of this chapter. So we'll have a review on the introduction of engine terminology, and then air standard Otto cycle, air standard diesel cycle, and then modeling gas turbine power plants, and then air standard Brayton cycle. So I think I give you an introduction about this sub-chapter in THERMO 1. And then this is the new sub-chapter in THERMO 2. So we will discuss air standard dual cycle, and then regenerative gas turbines. The idea is similar to the regenerative option in the vapor power cycles. And then regenerative gas turbines with reheat and intercooling. And then gas turbine based combined cycle. Okay, so we also have a combined cycle in this chapter. And then integrated gasification combined cycle power plants. And the last topic will be gas turbines for aircraft propulsion. Let's have a review on the introduction of engine terminology. The feature on the right side here is showing the simple schematic of an internal combustion engine. So it has several key parts. One is here is the cylinder wall, or usually people also call this cylinder blocks. And then the top part of the cylinder block is usually it's called cylinder head. So in this feature, and then we have two valves here. One is the intake valve, second one is the exhaust valve. So both valves control the mass flow in and out of the combustion chamber. And then we have also a spark plug or fuel injector at the cylinder head. So if it is a gasoline engine, which based on the Otto cycle, then it is a spark plug. If it is a diesel engine, then it will be a fuel injector. And then we have a piston here. So the piston moves up and down. So the piston does a reciprocating motion here. And then the piston is connected to the crank mechanism here through the connecting rod here. So this one, this is the connecting rod. Okay. The crank mechanism converts the reciprocating motion into the rotary motion, and then it will be connected to the shaft, and finally it will go to the wheel to drive our vehicle. So the way it's worked, depending on the number of stroke, so either we will have 4 stroke to complete the thermodynamic cycle, or 2 stroke to complete the thermodynamic cycle. So in 4 stroke, we have the intake stroke. So in this intake stroke, the intake valve opens, and then the fresh mixture enter the chamber. The piston move down, okay, and then once the piston is at the maximum location at the bottom side, it will move back, so it's move up, and then the intake valve close, and then there'll be a compression there. So this is the second stroke, so which is the compression stroke. And then as the piston approach the top center, either the fuel is injected if it is a diesel engine, or the spark plug ignite, then it will initiate the combustion. Okay. And then the piston move down again, the chamber volume increases, and this is the third stroke, which is called the expansion stroke or the power stroke. Because of the combustion, the cylinder pressure and temperature increases, so it's generate a power that is transferred to the piston and then transferred to the crank mechanism to do a work there. So from this reciprocating motion, it is converted into rotary motion by this crank mechanism. And then once the piston hit the bottom side of the chamber, it will move up again, doing the 4th stroke, and the exhaust valve will open so that the burn gas is discarded out of the system. On the left side, it is some nomenclatures for reciprocating piston cylinder engine. Now, one here is what is called bore. Bore is the diameter of the cylinder, so this one. And then stroke. Stroke here is the distance the piston move in one direction. So either the piston move down or move up. So from the initial point to the final point. So the distance is called stroke. When we talk about the engine size, engine displacement, or engine volume, so actually this is the volume of the cylinder. Okay, the next one is top dead center, or TDC, or sometimes it is also called TC, top center. This is the piston position where the cylinder volume is a minimum. So for this schematic, it is at this point. So this is the top dead center or top center, TDC or TC. The next one is clearance. This is the minimum volume. And certainly this is the minimum volume when the piston is at top dead center. Next one is bottom dead center or BDC. So this is the piston position where the cylinder volume is a maximum. So in the schematic, it is somewhere here. Okay. And then displacement volume. So I just mentioned this one. Displacement volume. So this is the volume swept out by the piston as it moves from TDC to BDC, or it moves from BDC to TDC. And when we talk about the engine size or the engine volume, whether this is 2 liter or 2.5 liter. So, or if you have a Jeep with 2 liter engine, so it means this is the displacement. So if the engine has 4 cylinders, so it means each cylinder has 0.5 liters in case the engine size is 2 liters. Okay, the next nomenclature, what is called compression ratio. Okay, so this is one of the most popular parameter in the powertrain or in the automotive area. So this is the volume at PDC divided by the volume at TDC. Okay, so it's mean this is the ratio of maximum volume over minimum volume. And then I did mention it that in a 4-stroke internal combustion engine, the piston executes 4 distinct strokes within the cylinder for every 2 revolutions of the crankshaft. So if you remember, we have an intake stroke, the piston moves down. So it's mean in the crank mechanism, it is like half rotation. Okay, so 180 degree. And then compression, the piston move up. So in the crank mechanism, they rotate another 180 degree. So it's mean it's one complete rotation. And then the third stroke, it's called power stroke. So this is another 180 degree of the rotation. And then exhaust stroke, another again 180 degrees. So it's mean we have another revolution of the crankshaft. So in a 4-stroke internal combustion engine, so the piston executes 4 distinct strokes, okay, for every two revolution of the crankshaft. So on the right side here is the PV diagram for a process inside an internal combustion engine with a 4-stroke. So we have the intake stroke. So let me put a number here. So it starts from this point. So at this ideal process, so intake valve opens when the piston is at top dead center, okay, and the exhaust valve close. So, okay, the intake valve open and then the piston move down toward bottom dead center. Therefore, the cylinder chamber volume increases. It's going to the right here. See here, this is the volume. Okay, and then the engine is conducting an intake stroke and the piston move down from top dead center until it hit the bottom dead center at this point. So I can put here is point number 1, here point number 2. Okay, and then at this point, for the ideal process, the intake valve close and then the piston move up again towards the top center, following this process line. And it's conducting a compression process. So the piston move up. So you can see in here that the line direction is going to the left. So it's mean the cylinder volume decreases. And then at some point before the piston hit the top center, either the spark plug will ignite the mixture or the fuel will be injected inside the cylinder chamber for the diesel case. So let's say this is the timing for the spark ignition or the timing for the fuel injection. We have combustion initiation at this point, and then there will be a combustion process inside the combustion chamber. The pressure and the pressure and temperature increases. So here you can see here the increase of pressure here, and then the piston move down again toward the bottom center, and this is the power stroke. So there will be an expansion from this high pressure and temperature gas. There is a transfer of energy from the thermal energy into the mechanical energy to the piston, and then it will be forwarded to the crank mechanism and so on. The piston move down, and then at some point here there will be a timing where when the exhaust valve open, okay, exhaust valve open, and the burn gas is discarded out of the combustion chamber. Okay, and then the piston move up again, going to the left. It means the cylinder chamber volume decreases, and the last process here is called the exhaust stroke. So we have point 1, 2. I can put here when this at top center is point 3, and then we have here somewhere here is point 4. So this is the actual PV diagram of an engine. In this thermodynamic 2 class, we will make some modeling or simplification assumption to have a simple PV diagram so that we can analyze this process manually. It's mean without the aid of computer. The other type of an internal combustion engine is a two-stroke engines. In these two-stroke engines, the intakes, compression, expansion, and exhaust operation are accomplished in one revolution of the crankshaft. So the intakes and compression strokes occurs for 180-degree crank rotation, and then the expansion and exhaust strokes occurs for another 180-degree crank rotation. Internal combustion engines undergo mechanical cycle, so it means we have a crank rotation there. We have crank rotation and then transfer this rotation power finally into the wheel. So it means they undergo mechanical cycle, but the cylinder content do not execute a thermodynamic cycle. So if you look at your car engine, it's suck in a fresh air, okay, and then at some point the fuel is introduced to the stream, and there will be a combustion, and then the burnt gas will be discarded out of your car engine. So it means this burnt gas doesn't go back into your engine again to conduct another cycle. So it means it does mechanical cycles, but it doesn't do a thermodynamic cycle. Another parameter, this is also important when we deal with an internal combustion engine, is mean effective pressure, or MEP. The MEP is the theoretical constant pressure that if it acted on the piston during the power stroke would produce the same net work as actually developed in one cycle. Okay, this is a very important definition. So this is the theoretical constant pressure that if it acted on the piston during the power stroke, okay, so it's only during the power stroke, so it means one piston movement from top center to the bottom center would produce the same net work as actually developed in one cycle. So we have intake stroke, compression stroke, power stroke, and exhaust stroke. And this is the formula to estimate MEP, formula 9.1. So MEP equal to net work for one cycle over displacement volume. This is because the piston move from top center to bottom center. Now let's take a look on how can we analyze the process inside the internal combustion engine. A detailed study of the performance of a reciprocating internal combustion engine would take into account many features. We have air going into the engine, and then at some point there will be a fuel introduction, so there will be a mixing process. And if we use a gasoline or diesel, so the fuel phase is liquid, so there will be a evaporation process inside the engine, and then at some point there will be a combustion process. This is a very complicated process, and then there will be a chemical process, and then conversion of the chemical energy into the thermal energy, and there will be a transport of the species, and so on and so on. So to conduct elementary thermodynamic analysis of internal combustion engines, considerably simplification is required, especially in this class. In THERMO II class, we will apply the simplification to enable us doing the analysis manually without the help of the computer. So one procedure is to employ an air standard analysis having the following elements. So it's mean here we will use air standard analysis. So in this air standard analysis, a fixed amount of air, okay, so a fixed amount of air modeled as an ideal gas is the working fluid. So we will ignore no fuel inside, or we do have the fuel, but we will assume that the fuel properties is the same as the air properties, so that we can assume that the whole mixture composition is 100% air. And then the combustion process is replaced by a heat transfer from an external source. So no combustion process at all, so in this analysis. So rather we'll assume there will be a Q in entering the internal combustion engine. And then there are no exhaust and intake processes as in an actual engine. So we'll assume that this intake process and exhaust process occurs in a simplified way. And then the last one is that all processes are internally reversible. Okay, internally reversible. So it's mean sigma equals to 0. And then further assumption, we can also use a method that's called cold air standard analysis. So in this cold air standard analysis, the specific heats are assumed constant at their ambient temperature value. So it means Cp and Cv and thus K is the specific heat ratio, are constant. With air standard analysis, so we avoid dealing with the complexities of the combustion process. I did mention it previously, and the change of the composition during the combustion process. So imagine initially you have only O2 and then N2 and then fuel. It can be C7H16 if it is N-heptane or isooctane, so it is C8H18. Or if it is a natural gas mainly consisting of methane, then it will be CH4. So in the initial combustion, they have those species, and then after the combustion process occurs, we will have a lot of burnt gas species. So CO2, CO, CO3, or C2H2, C2H4, and then phosphorus CO, OH, and so on. So it has a lot of combustion species there. So by using air standard analysis or cold air standard analysis, we avoid the complexity of the combustion process. And then an air standard analysis simplifies the study of internal combustion engine considerably. So, and then values for the mean effective pressure and operating temperature and pressure calculated on this basis may depart significantly from those of actual engines. So yeah, because we apply a lot of simplification here. Still, insights concerning actual performance can result with such an approach. So it's mean you can still use this approach just for doing a qualitative analysis, but not a quantitative analysis. You can still see the trend, so you can still see what will be the combustion efficiency or what will be the engine efficiency if we increase the conversion ratio. With this simplified analysis, you can still get the correct trend, but the absolute number might be wrong. Okay, so because we will use air as the working fluid for the process inside the internal combustion engine, so we will use some formula related to the air, and then the next one is air will be assume behaving an ideal gas. So we will use ideal gas equation of state. So you can see in this slide equation 3.32 and equation 3.33. So this is the formula for ideal gas equation of state. So PV equal to RT, or if you multiplied it by mass on both sides of equation 3.32, you will have PV. V is the capital letter here, it means it's volume. So the unit is cubic meter, equals to M. M is the mass, time R. R here is the gas constant. So this is the gas constant for air. So it means it is R0 over the molecular weight of air. So R0 is the universal gas constant. So 8.314 kilojoule per kilomole Kelvin. And the air molecular weight is 28.97 kilogram per kilomole. And then to calculate the change of internal energy and enthalpy, so we will use equation 3.40 or equation 3.43, and then we can simplify the way to get this integral by looking at two different conditions here. So on the left side, if we assume that the specific heat value are constant, so it's mean Cv and Cp here can be put outside of the integral here, then we will have equation 3.50. This is to estimate the change of the internal energy, so specific internal energy, or equation 3.51 to estimate the specific enthalpy. So specific enthalpy change here equal to Cp times delta T. And then if we doesn't assume constant specific heats, which means they are variable specific heat, then we will need to use table A22 for air, okay, or A22E for air on British unit, okay, or we can use table A23 in case the working fluid is not air, okay. So in table A22 you will have air table. In the first column, I believe it is a temperature column, and there will be two columns, one for internal combustion engine, second one is, one is for the internal energy, second one is for the enthalpy, and for sure there are other columns for other parameters like VR, PR, and so on. So once again, this is important. If we assume Cp or Cv are constant, so we use equation 3.50 or 3.51. If Cp and Cv are not constant, so we use this method. So we use table A22 or A23 to get the specific internal energy or specific enthalpy. And then the next one, to estimate the change in entropy. So we have formula 6.17 or 6.18, and then to get this number, the change in entropy, we have two options. On the left side is in case the specific heats are constant. On the right side is in case the specific heats are not constant. So we have equation 6.21 and 6.22, or we use equation 6.20a to get change in entropy for variable specific heats. And if you check the equation sheets in the blackboard, I include all of this formula there, okay. And then The next one is the correlation that we will use. So it also depends on the value of the specific heats. If specific heats are constant, so we use this formula. Okay. So for example, equation 6.43 here is showing the correlation between temperature ratio to the pressure ratio. K here is the Cp over Cv, and the number is available in table A20. And then if the case has a variable specific heat and for air only, you can use equation 6.41 or 6.42 to get the correlation between the pressure ratio and PR, or the specific volume ratio and VR. PR and VR are available in table A22. Okay, you can check it. Okay, the next topic is air standard Otto cycle. So this Otto cycle is the baseline or the reference cycle for a gasoline engine cycle. The air standard Otto cycle is an ideal cycle that assumes heat addition occurs instantaneously while the piston is at top dead center. Okay, look at this PV and TS diagram. So we have a starting point here at point 1. So this is the start of the compression process. So the line connecting point 1 and point 2 here is an isentropic compression line. So in this case, air is compressed as the piston moves from bottom dead center to top dead center. And this process occurs isentropically. So it means the entropy is constant. If you look at on the TS diagram, the line connecting point 1 to point 2 here is a straight vertical line. So it means S1 equal to S2. Okay. The second process, this is to represent an Otto cycle. This is process 2 to process 3. This is a constant volume process. You can see in the PV diagram that point 2 is connected to point 3 by a straight vertical line. So it means V2 equal to V3. So this is a constant volume process in which heat transfer to the air from an external source occurs while the piston is at top dead center. So the piston stay there, so it doesn't move, it is stay there. It is at point A here, at top dead center point. This process is intended to represent the ignition of the fuel-air mixture and the subsequent rapid burning process. So from point 2 to point 3, there will be a heat transfer or heat addition coming into the working fluid here. This is Q in, and it is occurs at constant volume. Okay. The next process, it is a process line connecting point 3 to point 4. It is an isentropic expansion, or sometimes it is also called a power stroke. Isentropic, so it's mean S3 equals to S4. Okay, and then the last process is a constant volume process in which heat is rejected from the air while the piston is at bottom dead center. So piston is at point B here. The process line here is the line connecting point 4 to point 1. So it is a straight vertical line in the PV diagram. So it's mean V4 equal to V1. Okay, this is a schematic of the 4-stroke process. So we have an intake process here. So the fresh mixture entering the combustion chamber. So this is the combustion chamber, okay? And then this process ends when the piston hit bottom center at this one, okay? And then the piston move up again, and then compressing the mixture inside the combustion chamber. So you see the piston move up, and then the cylinder volume on the combustion chamber volume decreases, and then you can see also the intake valve closed there, and we have a combustion process there, increasing pressure and temperature, and then the piston move down again toward BDC. So we have a expansion process or expansion stroke, or also called power stroke here. Okay, so this one. And then the last process here, it's called exhaust stroke. So the piston move up and then pushing the burn gas out of the combustion chamber, and the exhaust valve open, you can see in here, and then the burn mixture exit the combustion chamber, and then piston move down again, going back again to the intake process. Okay, since the air standard Otto cycle is composed of internally reversible process, area on the TS and PV diagram can be interpreted as heat and work respectively. Okay, so let's take a look first in the TS diagram. So the area surrounded by point 2 and then 3 and then A and then B and then 2 here represent the heat added per unit of mass, and then the area surrounded by point 1, point 4 and then A and then B and 1 again. This represent the heat rejected per unit of mass, and the difference of these two heat is net heat, which equal to the net power. And in this TS diagram, it is represented by the area inside the process line. Okay. And then in the PV diagram, okay, the area surrounded by point 1, 2, okay, and then A, B, 1 again. This represents the work input per unit of mass during compression. Okay, during the compression, there will be an energy going into the system. Okay, and then the area surrounded by point 3 and then point 4 and then B, A, 3 again. This is the work done per unit of mass in the expansion process or in the power stroke. And the difference and the net work here, it's what is called the work developed by the engine, and it is represented by the enclosed area. Okay, this one. Okay, so the enclosed area of each feature here, either in a PV diagram or TS diagram, can be interpreted as the net work output, or equivalently the net heat added to the system. Okay, next one is looking at cycle analysis. So we have a PV and TS diagram here. So two processes in which there is work but no heat transfer are process 1, 2 and process 3, 4. Okay, 1, 2 here is the compression process. So there is work there, work coming into the system. And then process 3, 4 there is a work as well. So the work produced by the system, but no heat transfer. Okay, and then two process in which there is heat transfer but no work. So this is process 2, 3. So there is a Q in there coming from outside, coming from the fuel combustion. And then process 4, 1 is the heat rejected from the system going into the environment. So expression for this energy transfer are obtained by reducing the closed system energy balance, assuming delta KE, kinetic energy, and delta PE, potential energy, equal to 0. Then you will have correlation 9.2. So to get the compression work, it is a compression work per unit mass. It is U2 minus U1. Remember, this is a closed system, so there is no mass flow in and out of the system. So we use internal energy parameter here. And then the work produced during the expansion stroke, it is U3 minus U4. This is per unit mass once again. And then the Q added to the system per unit mass, it is U3 minus U2. And then the heat rejected out of the system per unit mass, it is U4 minus U1. And then to get the network, either we can get it from the difference between the work produced by the system minus the work required by the system for doing the compression. So W34 minus W32 here, all per unit mass. It's equal to U3 minus U4 minus U2 minus U1. Or we can get this network from the net of the heat. So this is the Q in minus Q out. And you can see there that if you modify the position of the U slightly, this formula are the same. And then the thermal efficiency is the ratio of the net work of the cycle to the heat added. So once again, so when we talk about the efficiency, it is the ratio of what we gain. So here is the net work over what we pay. So here is the Q in. So this is coming from the fuel energy, and you pay this fuel. So we use equation 9.3 to estimate the thermal efficiency of the internal combustion engine. So this is 1 minus U4 minus U1 over U3 minus U2. So once again, equation 9.3 here is used to estimate the thermal efficiency of the internal combustion engine based on the Otto cycle. So it's mean the heat addition occurs during a constant volume process. And then when air table data are used to conduct an analysis involving air standard Otto cycle, the specific internal energy value required by equation 9.3 in the previous slide can be obtained from table A22 or A22E for a British unit. And then the following relationship based on equation 6.42 also apply to the isentropic process of process 1 to 2 or 3 to 4. So you can use these two correlation, 9.6 and 9.7, in case we assume that K is constant. So it's mean this is cold air analysis space. So you can get the correlation of the temperature ratio to the volume ratio. This one is the power number, so K minus 1. Once again, K is the specific heat ratio, so this is Cp over Cv. Or you can get the correlation of the temperature ratio between T4 and T3 from this volume correlation. And if you see V3 over V4, this is, so V3 over V4, this is also equal to V4 V4 over V3, and V4 over V3 here is actually compression ratio, R here. The next one is looking at the effect of compression ratio on performance. For you who loves automotive might know that increasing compression ratio improve the engine efficiency or improve the fuel economy. In daily speaking, it's called mileage per gallon for a car. So higher compression ratio improve mileage per gallon of your car. So the Otto cycle thermal efficiency increases as the compression ratio increases. You can see in the PV and TS diagram here. So in the TS diagram, we increase the compression ratio, so it's mean the pressure at the end of compression stroke is increased from 0.2 to 0.2 primes. So an increase in the compression ratio here changes the cycle from 1, 2, 3, 4, 1 to 1, 2 primes, 3 primes, 4 ones. And then we can analyze the performance of this new compression ratio. In this case, we use cold air analysis, so we assume that CV is constant. From the thermal efficiency, we know that the formula, I believe, is 1 minus U4 minus U1 over U3 minus U2. Because we assume that CV is constant, you can replace U4 by CVT4, you can replace U1 by CVT1, and so on, so you will get this formula. Okay, and then we can drop out this CV, so you will get this formula. And then we know from equation 9.6 and 9.7 that T4 over T1 equals to T3 over T2, and then you can simplify the thermal efficiency correlation by having this one. Thermal efficiency equals to 1 minus T1 over T2. And then by introducing equation 9.6, it is in the previous slide, so you can get equation 9.8. So this is the thermal efficiency as a function of the compression ratio, R, and K. K here is the specific heat ratio. So in this case, K is constant. So you have this correlation 9.8, and you can use your Excel to plot how does R here influence eta. And this is the result. You can see in here that as R is increased, the thermal efficiency also increases. And again, this is the reason why in engine design we try to maximize the compression ratio as possible, and for sure there is some limitation there. For example, like in gasoline internal combustion engine, it is limited by knocking, and then in diesel combustion we do not have knocking, but it is limited by the material strength. So having higher compression ratio means also higher compression pressure, and thus also higher combustion pressure. Let's take a look on this example. The temperature at the beginning of the compression process of an air standard Otto cycle with a compression ratio of 8 is 540 Rankine. The pressure is 1 atmosphere and the cylinder volume is 0.02 cubic feet. The maximum temperature during the cycle is 3600 Rankine. So this is T3. The question: determine the temperature and pressure at the end of each process of the cycle. and then the thermal efficiency, and the last question is the mean effective pressure in atmosphere. Okay, this is the PV and TS diagram. So point 1 is at the beginning of the combustion process, and then point 2 is at the end of the combustion process. The heat addition occurs between point 2 and point 3, so this is at constant volume. So we have a Q in here. And then point 3, the temperature is given there, 3600 degree Rankine. And then below here is the engineering model or assumption. So the air in the piston cylinder assembly is the closed system. And then compression and expansion process are adiabatic. Okay, compression and expansion process are adiabatic. And then combined with the assumption that it is internal reversible process. So point 1 and 2 is connected by a straight vertical line in the TS diagram, so it means S1 equal to S2. Similarly, S3 equal to S4. So assumption number 3, all processes are internally reversible, all process, and then the air is modeled as an ideal gas, and then we can ignore the impact of kinetic and potential energy change. Okay, the first step is to determine the properties at individual point. So we start with point number 1. Temperature is given, 540 degree Rankine. So this is air. The unit is British unit. So you use table A22E. So go to this table and try to find out the temperature at 540 degree Rankine. So you should get U1 of 92.04 BTU per pound, and then VR1. This will be used to determine the properties at state 2. So VR1 is 144.32. And then by using this correlation, so the correlation between V2 over V1 to the VR2 over VR1. So V2 over V1 is the reciprocal of compression ratio. So V2 over V1 is 1 over R. So VR1 is 144.32, R is 8, so you should be able to get VR2. And then go back again to table A22E, locate the VR of 18.04, so for sure this number I think won't be the same as the one listed in the table, so very probably you need to do interpolation. So you have 18.04 and then find out the two lists of the VR that bracket this 18.04. So by doing the interpolation, you will get T2 of 1212 degree Rankine and U2 of 211.3 BTU per pound. And then to get P2, you can apply the ideal gas correlation. So in this case, we have P1 V1 over T1 equal to P2 V2 over T2. Then you should be able to get P2 here. Okay, so P1 is given, V1 is also V1 over V2 is the compression ratio, and then T1 is 540 degree Rankine, and then T2 is 1212 degree Rankine. You should be able to get P2. You can also get P2 by using the correlation between pressure ratio to the PR ratio. So this one. So P1 is given, and then PR1 you can get it from table A22E, and then PR2 you should be able to get it similar to the way we got T2 and U2. So maybe this process will take slightly longer because you need to do an interpolation for getting PR2, but either way should work. So either you use ideal gas formula or you use this correlation. And then since process 2, 3 occurs at constant volume, you can also use ideal gas formula here. So once again, you have this formula, but in this case, V2 equal to V3, so the volume parameter will cancel out. So you only get the correlation of P, let's say P2 over T2 equal to P3 over T3. So you can get P3 using this correlation. Okay, P2 is 17.96 atmosphere, T3 is given 3600 degree Rankine, T2 has been calculated 1212 degree Rankine, so you should be able to get P3. And then at T3, this is 3600 degree Rankine, you can get a U3 and VR3 from the same table. Okay, and then the process connecting point 3 to point 4 is an isentropic process. You can use this correlation to get a VR4. So here is 5.16. And then going back again to the table, with this VR4 data, you should be able to get what is H4 and other parameter. Okay, so in this case, you should be able to get T4 of 1874 degree Rankine. U4 is 342.2 BTU per pound. Okay, and then pressure at P4, you can use this correlation. Okay, or you can also use the correlation between pressure ratio and PR ratio. Okay. Okay, good. So we have completed the first question about specifying or determining the properties at each operating point. And then the second question is the thermal efficiency. So the eta is 1 minus here, the ratio of the heat. So Q for 1 here is the heat rejected, and Q23 is the heat added to the system. And you have this formula. And from the answer of A, we got U4, U1, U3, U2, and so on. Just plug in all the number in this correlation, you should get the efficiency. So this is 51%. So it's pretty high for a typical internal combustion engine efficiency. And then C is calculating mean effective pressure here. So first we need to calculate what is the net cycle work. Okay, so W cycle here is the work generated by or produced by the system during the expansion stroke minus the work needed by the system during the compression stroke. Okay, so this is m dot time U3 minus U4 minus the compression work is U2 minus U1. Mass is not given here, so we need to calculate the mass inside the engine. We can use 0.1 here to calculate the mass. So pressure is given, temperature is given. Pressure, I believe pressure is calculated, and then volume is given, and then temperature is given, and then R here is just R0 over M, or here is R with over bar. So we have all number here, should be able to get the mass inside the engine. So 1.47 times 10 to the power of minus 3 pound. And then we plug in the number to get the net work there, 0.382 BTU. So once we got this network, we can get the MEP. So MEP is the network over the displacement. So V1 minus V2. So what you need to pay attention here is that we need to do, or we need to apply two number here representing the unit conversion. One is to convert the unit from BTU to feet pound force. So multiplied by 778. Second one is the conversion from or the conversion between square feet and square inch. Okay, so you will get the MEP of 8.03 atmosphere. The next topic is the air standard diesel cycle. So this standard diesel cycle is the reference cycle for a diesel engine cycle. The air standard diesel cycle is an ideal cycle that assumes heat addition occurs during a constant pressure process. Okay, so this is the keyword, constant pressure process. This differentiates the diesel process from the Otto process. So in the Otto process, or in the Otto cycle, in the previous topic, the heat addition occurs during a constant volume process. So in this diesel cycle, the heat addition occurs during a constant pressure process. Okay, and this constant pressure process start with the piston at top dead center point. So below here is the PV and TS diagram. So we have point 1 here is at the beginning of the compression process, and then we have point 2 here is at the end of the compression process. The heat addition occurs during a constant pressure process. So this is the process line connecting point 2 and point 3. This is the Q in. See here, this is a straight horizontal line, and this is the pressure line, pressure axis. And then the TS diagram is on the right side. So we have point 1 and then point 2. This occurs at constant pressure. So P equal to constant. And then from 3 to 4, here is the expansion process. So if you look at back on the PV diagram here, during the heat addition, the system also does a work here from point 2 to point 3, and then 3 to 4 is the continuation of the expansion work here. Okay, so in the TS diagram again, you have 3 to 4 here is the expansion process, and then 4 to 1 here is the process at a constant volume. Okay, constant volume. And see here that the slope of the constant pressure line is smaller than the slope of the constant volume line. For the cycle analysis, so again we have PV and TS diagram on the top right slide here. So process 2, 3 here involves both work and heat. So once again, there is a change of volume from point 2 to point 3. So it's mean PdV is not 0. Okay, but we do have information that there is a Q in here. So from point 2 to point 3, we have the heat transfer there as well as the work. So the work is here is W23, the work per unit of mass here is the integral PdV. So this is from point 2 to point 3. This is P2, pressure constant, P2 times V3 minus V2. Okay, and then you can apply an energy balance here for representing process from point 2 to point 3. So delta U equal to Q minus W. So you have this formula. And then by doing some manipulation a little bit on this formula, so you have Q23 here equal to H3 minus H2. Okay, so this is different from the Q in formula for Otto cycle. So in diesel cycle, Q in is Q in per unit of mass is the enthalpy difference. between 0.3 and 0.2. And then the heat rejection, it is Q41. The formula here is the same as the one for the air standard. Oh, same as the one for the Otto cycle. Okay, the thermal efficiency is the ratio of the network of the cycle to the heat added. So this is W cycle over Q23. So Q23 is what we pay. So this is coming from the fuel combustion. And then you can modify the equation to be like this: 1 minus Q41 over Q23, equation 9.11. So this is the formula for the thermal efficiency of the diesel cycle, ideal diesel cycle. And some other formula that we can have here is the ratio of the volume to the ratio of the VR. So here we have VR2 equal to V2 over V1 times VR1, and V2 over V1 is the reciprocal of the compression ratio. And then you can also use this formula to get the ratio of V4 over V3. So this is R over RC. So RC here is V3 over V2. Okay. Do we have RC? Oh, okay, here. V3 over V2. Sometimes it is also called cut-off ratio. Okay, so we have R and we have RC for this ideal diesel cycle. And another formula that you can use is to get the T3 from the ratio of the volume and the given T2. And then this is the formula to get VR4 from the volume ratio of V4 over V3 and VR3. How about the effect of compression ratio on performance for this ideal diesel cycle? So by doing a similar way to determine the compression ratio effect on the efficiency for ideal Otto cycle, we can also do the same thing. So it is based on the cold air standard basis, and you will get equation 9.13 to get the correlation of the compression ratio plus RC here, the cutoff ratio, to the efficiency eta. And then if you plot this formula, you will get this figure. And keep in mind that RC here is the cutoff ratio. So this is the ratio between V3 and V2 for the Otto cycle. V2 equal to V3, so it's mean RC equal to 1. Okay, RC equal to 1. So for the Otto cycle, looking back again on the previous slide, this one equal to 1. Okay. So look at again this chart. So you have thermal efficiency as a function of the compression ratio. For RC equal to 1, so it's mean V2 equal to V3. So you have Otto cycle here. And then as we increase RC, then the efficiency drops for a given compression ratio. So you see here, if I have compression ratio of 15, and then by increasing RC, the thermal efficiency decreases. So you can see in here, for the same compression ratio, Otto cycle has higher thermal efficiency than the diesel cycle. But it is counterintuitive from what we saw in the dialog speaking or in the actual engine. So we know that diesel engine is more efficient than gasoline engine. And the reason for that is because diesel engine usually operate at a very high compression ratio. And why it's operate at very high compression ratio? Because there is no knocking issue in diesel engine. Let's have a look on this example. At the beginning of the compression process of an air standard diesel cycle operating with a compression ratio of 18, so it is 18, in the previous cycle we only have 8, although it is an example, but the number there represents the trend of the compression ratio between Otto cycle and diesel cycle. So a compression ratio of 18, the temperature is 300 Kelvin, and the pressure is 0.1 megapascal or 1 bar here. The cutoff ratio for the cycle is 2, so this is V3 over V2. The question, determine the temperature and pressure at the end of each process of the cycle. And then B is the thermal efficiency, and C is the mean effective pressure in megapascal. Let's have a look on the solution of this example. This is the PV and TS diagram. So point 1 is at the beginning of the compression process, and then pressure is given there, 0.1 megapascal, temperature is 300 Kelvin, and point 2 is at the end of the compression process, and then RC is given, so V3 over V2 equals to 2, and then this one is the engineering model assumption, so a closed system, and then adiabatic process for the compression and expansion, and then internal reversible process for all, and then we can model air as an ideal gas, and then we can ignore the impact of kinetic energy and potential energy change. The first step is to determine the properties at each operating point. So at point 1, we have temperature of 300 Kelvin. So this is SI unit, so we will use table A22. So go to the temperature of 300 Kelvin. You will get a U1 of 214.07 kilojoule per kilogram. VR1, this will be used to determine VR2. So VR1 is 621.2. And then by using an isentropic correlation, we will get VR2 of 34.51. And then you go back again to table A22 to get T2 and H2 based on this VR2 value. And you will need to do interpolation there. And then for P2, either you use this ideal gas formula, or you can use this formula. So getting P2 from PR2. And as I mentioned to you in the previous slide, this method might take slightly smaller times because you don't need to do an interpolation. And then at point 3, we have we can apply. So at point 3, we can apply ideal gas correlation. In this case, between point 2 and point 3, the pressure is the same. So pressure parameter will cancel out. So you have only this parameter in the equation. So T3 equal to V3 over V2 times T2. So V3 over V2 is RC. Okay, RC is given there, 2. Here. So you will get T3, and then once you get T3, you go back again to table A22 to get H3 and VR3. And you need to do interpolation here. Okay, and then we use volume ratio and VR ratio to get VR4. Okay, and here you need to do some manipulation here. VR4 equal to V4 over V3. Okay, but we don't have the value of V4 over V3, but you can manipulate V4 over V3 by using this formula. So V4 over V3 equal to V4 over V2 times V2 over V3. V4 over V3 is the compression ratio, and V2 over V3 is the reciprocal of RC. Okay, so you have all number. You should be able to get VR4 finally. So 35.73. Then you go back again to table A22, sorry, to get U4 and then T4. And then to get P4, you need to use ideal gas correlation here. So P4 is 0.3 megapascal. Second question is the thermal efficiency. So I believe it should be easy because you have all parameters here. So efficiency is 1 minus, so U4 minus U1 over H3 minus H2. 57.8%. Okay, so it's higher than the one from the first example. Okay, and then the next one is to calculate MEP. Okay, so you need to get what is the net work, and then V1 minus V2, it is equal to V1 times 1 minus 1 over R. It's just small manipulation here. Okay, so to calculate network, this one is per unit of mass. You can get it from the net heat. So this is Q23 minus Q41. Everything here is per unit of mass. Okay, so you plug in all the number here, you will get that net work per unit of mass is 617.9 kilojoule per kilogram. Okay, and then you can get V1, the specific volume here. So because T1 is given, and then P1 I believe is also given there. So you will get the specific volume here is 0.861 cubic meter per kilogram. Okay, so we have this number and we have this number. You should be able to get the MEP. So the MEP is 7.6 bar. Next topic, air standard dual cycle. So the previous cycles, either this Otto or diesel cycle, doesn't represent the actual cycle in the engine. And one of the approach or one of the cycle, ideal cycle, that's maybe it's close to the actual engine cycle is this air standard dual cycle. So in this dual cycle, the heat addition occurs at two processes here. So one is between point 2 and point 3. So we have heat addition here. Okay, we have heat addition here. This is, let's say, I call this Q1. And then you have another heat addition here. It is Q2. Okay, that's why it's called dual cycle. So the heat addition occurs at two processes there. Okay, constant volume process and constant pressure process. In the TS diagram, see here, so you have point 3, and then point 4. Okay, the first one is at constant volume, second one is at constant pressure. And then the work required to compress the mixture, this is W12. See there, this U1 minus U2, and then this one is negative. But if you want to get everything positive, you can reverse this one. So W12 is U2 minus U1. Okay, and then Q23, here is the heat addition at constant volume. So this is U3 minus U2, and then you have the first work here from the process connecting point 3 and point 4. W34. It is at constant pressure at P3. So the W34 here is P3 times volume different. So this is V4 minus V3. And then the second heat addition, Q34 here, is m dot or m times H4 minus H3. See here, we use enthalpy. Okay, and then the second work generated by the system, this is W45. This is m times U4 minus U5. Okay, and this one is the heat rejected from the system. Once again, if you want to get a positive number, this Q51 is U5 minus U1. And this is the thermal efficiency for the dual cycle. Okay. And this PV diagram, if you look at the shape of this PV diagram, this is close to the actual PV diagram of an engine. See here. So where the heat addition occurs at both constant pressure and constant volume. Okay, it's close, although it's not the same. Okay, and here 5 internally reversible process that compress this dual cycle. So we have isentropic compression, we have constant volume heat addition, constant pressure heat addition, and then isentropic expansion, and the last one is constant volume heat rejection, so 0.5 to 0.1. Okay, let's have a look on the example of this dual cycle. At the beginning of the compression process of an air standard dual cycle with a compression ratio of 18, the temperature is 300 Kelvin, the pressure is 0.1 megapascal. And then the pressure ratio for the constant volume part of the heating process is 1.5 to 1. The volume ratio for the constant pressure part of the heating process is 1.2 to 1. Determine the thermal efficiency and the mean effective pressure in megapascal. This is the schematic of the PV NTS diagram. So pressure at 0.1 is given there, 0.1 megapascal. Temperature is also given, 300 Kelvin. And then compression ratio is 18. So V1 over V2 is 18. And then P3 over P2 is given 1.5. And then V4 over V3 is also given 1.2. And then this one is the assumption or engineering model. So it's closed system, and then adiabatic process for compression and expansion, and then all process are internally reversible, and then the working fluid is air and can be modeled as an ideal gas, and then we can ignore the effect of kinetic and potential energy change. And this is the solution. Like in the previous two examples, we need to specify the properties at each point. So 0.1, 0.2, same thing. You use the same method as the one in the previous two examples. So you will get U1, U2, and then T3 here, and then doing interpolation, you will get H3, and then process 3 to 4 occur at constant pressure, and the volume ratio is given 1.2. You will get T4, and then once you get T4, you can go back to the table A22 to get H4 and VR4, and then process 4 to 5. This is an expansion process, so it is isentropic process. You can use this correlation. Okay, and then this just showing the ratio of the volume. So V5 over V4 equals to V5 over V3 times V3 over V4, and V5 over V3 is the compression ratio, and then V3 over V4 is given. Okay, so you can see here compression ratio is 18 and V3 over V4 is 1 over 1.2, and this is given in the problem. You will get 15 for the V5 over V4, then you get VR5 84.135, and then doing the interpolation you will get U5 475.96 kilojoule per kilogram. Once you get all properties at each point, you are ready to get the thermal efficiency by plugging all the number there. You will get the thermal efficiency of this dual cycle 63.5%, and then similarly you do the same thing here to get the mean effective pressure. Make sure that you use the same unit. Okay, you will get the mean effective pressure of 5.6 bars.